Okay, I'm going to just set these two word problems up because I've shown you plenty of exercises on how to solve simplex problems. So a contractor is planning to build a new housing development consisting of colonial houses, split-level houses, and ranch-style houses. A colonial home requires 0.5 acres of land, 60,000 capital, 4,000 labor hours to construct, and returns an estimated profit of $20,000. A split-level home requires a half acre of land, 60,000 capital, 3,000 labor hours to construct, and returns an estimated profit of $18,000. A ranch-style home requires 1 acre of land, 80,000 capital, 4,000 labor hours to construct, and returns an estimated profit of $24,000. Now there are only 30 acres of land available, 3.2 million in capital available, and 180,000 labor hours available. So how many homes of each type should be built to maximize profit? And what is the maximum profit? So to solve this, I'll let x1, x2, and x3 represent the number of colonial, split-level, and ranch-style homes. So x1 is the number of colonial homes, x2 is the number of split-level homes, x3 is the number of ranch-style homes. So first of all, let's talk about our profit. We want to maximize our profit, and if you go back and read through the problem, you can see that it tells you how much each home will profit in here. I missed one. There it is. Whoops, no, that's not it. There it is. Okay, so here's the profit. So your X1 homes will profit $20,000. Your X2 homes will profit $18,000 each, and your X3 homes, that's not profit. Sorry, it's this one, will profit $24,000 each. So let's get that off of there. Okay, so your total profit would be 20,000 X1 plus 18,000 X2 plus 24,000 X3. And now let's talk about the land. Now we know that each of your X1 homes requires a half acre of land, each of your X2 homes requires a half acre of land, and each of your X3 homes requires 1 acre of land. So the total land usage will be 1/2 times X1 plus 1/2 times X2 plus 1/2 times X3, and that has to be less than or equal to the 30 acres of land that's available. Now let's talk about the capital, 3.2 million in capital. Well, it tells you it's going to cost $60,000 for each X1 home, $60,000 for each X2 home, and $80,000 for each X3 home. So 60,000 X1 plus 60,000 X2 plus 80,000 X3 is going to be the total cost, and that's got to be less than or equal to the 3.2 million that's available. And then you only have 180,000 labor hours available, and it tells you in the problem that each X1 home requires 4,000 labor hours, each X2 home requires 3,000 labor hours, and each X3 home requires 4,000 labor hours. So if you add those three together, that's your total labor hours, and that has to be less than or equal to 180,000. Now make sure you scour the problem to make sure that there aren't any other constraints that you missed here, and I don't believe there are here. And so then at the end, don't forget to list your non-negative constraints. So this is setting up the linear programming model. Okay, now I'm not going to solve this, but I will give you the initial simplex tableau. So if you wrote the initial system for this and then put it in a tableau, it should look like this. And so I'm not going to solve it, but if you want to solve this for practice, you can go to your scratch paper and you can solve this for practice. And I can kind of get you started here. You're going to pivot on this column because negative 24,000 is the most negative indicator, and then you just have to figure out which one of these elements here that you're going to pivot on, and then you would go through the pivot. But the answer, I'll give you the answer. The answer is actually a profit of $1 million for X1 equals 20 acres, or X2 equals 20 acres, and X3 equals 10 acres. So actually that's not acres, I'm sorry, that should be homes. So it's the number of homes, not acres. So it's X1 equals 20 homes, X2 equals 20 homes, and X3 equals 10 homes. Okay, so my bad on that. So anyway, that's the solution to that one. Now, I've got one more here, and this says a candy company makes 3 types of candy: solid candy, fruit candy, and cream-filled candy, and packages these candies in 3 different assortments. A box of assortment 1 contains 4 solid, 4 fruit, and 12 cream, and sells for $9.40. A box of assortment 2 contains 12 solid, 4 fruit, and 4 cream, and sells for $7.60. A box of assortment 3 contains 8 of each and sells for $11. And then it tells you the manufacturing costs per piece of candy are 20 cents for each solid piece, 25 cents for each fruit, and 30 cents for each cream. And the company can manufacture up to 4,800 solid candies, 4,000 fruit candies, and 5,600 cream candies weekly. How many boxes of each type should the company produce in order to maximize profit? And what is their maximum profit? Well, this one's a bit more complicated because you're asked to maximize profit, but you're not actually given the profit per box. What you're given is you're given the revenue per box. For instance, in box 1, you know each box 1 sells for $9.40, so that's the revenue. But remember, profit is revenue minus cost. So if I can figure out what it costs to stock this box, remember in this box I have 4 solid candies, 4 fruit candies, and 12 cream candies. So let's look at what it costs me to stock a box of assortment 1 candies. So I've got solid candies, 4 of those, and it costs 20 cents to make each solid candy, so that's 80 cents. And then fruit candies, there's 4 of those in box 1, and it costs 25 cents to make each of those, so that's $1. And then there's 12 cream candies in each box, and it costs 30 cents each for each of those, so that's $3.60. So now if you add all of these up, that tells you the total cost per box is $5.40. And since we know the total revenue is $9.40, we can do $9.40 minus $5.40 and get that the profit per box is $4 per box. Now in box assortment 2 type, you have 12 solid candies at 20 cents each, so that's $2.40 cost. 4 fruit candies at 25 cents each, so that's $1 cost. And then 4 cream candies at 30 cents each, so that's $1.20 cost. So if you add those up, your cost for a box of assortment 2 would be $4.60. And in the problem it tells you the revenue per box 2, that type of box, is $7.60. So take the difference between these two values and you get that the profit for each box 2 is $3. And then in assortment 3, box 3, you've got 8 of each. So you've got 8 solids at 20 cents each, 8 fruit candies at 25 cents each, and 8 cream candies at 30 cents each. So if you add up those costs, they add up to a total of $6, and it tells you in the problem that the revenue for that type of box is $11. So if you take $11 minus $6, that gives you $5. So you're going to profit $5 per box for those boxes. So putting all this together, we know now that we want to maximize our profit, and we're going to profit $4 off of each box 1, $3 off of each box 2, and $5 off of each box 3. Now, but the constraints, I have to make sure that I don't go over the amount of candies that I can make per week. So remember, we can make up to 4,800 solid candies per week, and if you go back and look, your solid candies, notice you're going to need 4 solid candies for each box 1, 12 solid candies for each box 2, and 8 solid candies for each box 3. So 4 times x1 plus 12 times x2 plus 8 times x3 represents the total number of solid candies you're going to use, and that has to be less than or equal to the 4,800 solid candies you can make. Then you do the same thing for fruit. Each box 1 is going to require 4 fruit candies, each box 2 is going to require 4 fruit candies, and each box 3 is going to require 8 fruit candies. So 4x1 plus 4x2 plus 8x3 is the total fruit candies you're going to actually use, and that has to be less than or equal to 4,000. And then for your cream candies, you're going to have 12 cream candies each box 1, 4 cream candies in each box 2, and 8 cream candies in each box 3. So 12x1 plus 4x2 plus 8x3 is the total cream candies you'll use, and that it has to be less than or equal to the 5600. And I didn't see any other constraints in this problem, so those are the 3 problem constraints. And then don't forget to add in your non-negative constraints, and there you have it. There's the setup of that linear programming model. Now, I didn't give you the initial system, but if you add slack variables to each of these and then set up the initial system of equations, it will lead you to this as your initial simplex tableau. And so if you want to practice this problem, you can take this initial simplex tableau and apply the simplex method to it to get an answer. And so the answer is actually, you're going to have a profit of 2,850 when x1 is 200 boxes, x2 is 100 boxes, and x3 is 350 boxes. And of course, the slack variables, since all 3 variables entered, then the slack variables would be 0. Okay, so that's how you set up and solve, well, actually, mainly this was just setting up the problems. I'm leaving the solve part to you, but I did set up the initial simplex tableau for you, and then you can take that tableau and solve it and make sure that you can get the answers that I've got. So my final notes on the simplex, I've kind of mentioned this before, but how do you know if a problem has no solution? Well, just take a look at this. On this example, let's say this was my initial simplex tableau. Well, here I've got to pivot on the -5 because that's the most negative indicator. So if I'm going to pivot, I got to pivot here. But you can only use positive numbers above the -5 to get your pivot row. So since none of these 3 numbers are positive, then you can't choose a pivot row. So therefore, you have no solution. Because you can't just say, well, I'm going to move to another column, because you can't. You've got to stay with that column since that's your most negative indicator, and so you just can't move on. Now, can you do these tableaus on the calculator? Well, if you know how to do row operations on the calculator, you can actually do the simplex method on the calculator, but remember, the simplex method is doing row operations in a particular order. There's no shortcut key because the operations are not done in the same order as Gauss-Jordan elimination. Some of you might, what I'm saying is, some of you might be familiar with the RREF key on the calculator that solves systems of equations. But see, when we're solving these tableaus, we're not going through the same order that we do when we're solving systems of equations. So that's not going to lead you to the right answer. All right, well that concludes our discussion about solving standard maximization problems using the simplex method. And in the next section, I'll talk to you about how to solve standard minimization problems using the dual method.